Okay, so now we are glad to have one of the keynote speakers of this conference, Professor Ariel Caticha, from the Department of Physics of the University of Albany. So he will speak about quantum mechanics as a Hamilton killing flow on a statistical manifold. Please go on, Ariel. I think perhaps you're muted.
There, that's better?
Yes, yes, now we can hear you. Perfect.
Okay. Tell me if there are connectivity problems at some point, because I'm always having problems here.
I will let you know.
I would like to start by thanking the organizers for organizing all of this, which is not only a challenge, but also has turned out very, very nice results. We've heard some very, very good talks here. And for being particularly accommodating with the fact that my health played a little trick with me earlier in the week, and I managed to switch my talk to the end, and now I'm okay, still under the influence of drugs. But if you hear anything sort of weird in my talk, that's probably not the drugs, is that the talk is a little bit weird. Anyway, so let me see, let me start. Let me start by discussing a little bit of a preview of where it is that this talk is going. I would like to give you a list or classify. I mean, I'm sure you've seen this before. Classify the various interpretations of quantum mechanics so that you can see where the entropic dynamics approach would actually land. If you try to put various interpretations of quantum mechanics and classify them according to being realist or anti-realist, in the sense of are there the values of quantities are predefined, pre-existing, or whether they are created by the results of measurements, or whether the wave function itself is an epistemic construction, or the wave function is an ontic real object, then well, clearly you would not find any theories over here, because if nothing is actually real, what the wave function is, well, that doesn't lead you to any possibilities here. But here you can have, under epistemic size, you can have interpretations such as Copenhagen, cubism, maybe a model, whatever. You can have quite a few there. If you insist that the wave function be real, you have things such as the early Schrödinger approach, or the Bohmian interpretation, or many worlds, and so on. And finally, if you're going to have an epistemic wave function, but assume that there are underlying real variables floating around, statistical interpretations will get you there. Okay, one of the reasons I wanted to show this little table is that tables like this are very, very useful in sort of guiding your thought, but they're incredibly dangerous in that they sort of hint subliminally to the fact that these are all the possibilities. Well, entropic dynamics, which is the version of the approach to quantum mechanics that I favor, is something that lands somewhere in between here. Entropic dynamics shares with the Copenhagen interpretation, for example, or even with Einstein, the fact that the wave function is completely epistemic. It shares with the Bohmian approach the fact that the position of particles, or the values of fields, for example, are completely ontic. The positions of particles are real. They exist out there. On the other hand, it differs tremendously from the Bohmian interpretation in that the wave function is completely epistemic as opposed to being ontic. So I'm gonna land a little bit in here. Positions are real, but all other observables are actually, the values of all other observables are actually created by the act of measurement. So for example, energies or momentum or spin or all these other variables would land very much in the same box as the Copenhagen approach. Very good. So now let's see, what are we doing? The subject is quantum mechanics. And unlike most of the interpretations that I had listed before, the goal here is not to take the mathematical formalism and append an interpretation to it. The goal is precisely the opposite. We start with a more or less clear interpretation of what's going on, and then we derive a mathematical formalism that applies to it. So we're reconstructing the theory. In the traditional approach, the Hilbert space comes first, which raises all sorts of questions. Why indeterminism? Why quantum probabilities? Where does the Bohr rule come from? Why do we have two modes of evolution of the wave function? And the ultimate question, what's real and what's epistemic? Those are questions that are very, very relevant in a Hilbert space first approach. What we're going to do is an alternative approach in which probabilities come first. So many of these questions are answered from the very beginning. The theory is obviously deterministic because it's about probabilities and so on, as we will see. But this raises all sorts of other questions, different questions. If you start from probability, where do you get wave functions from? Why are there complex numbers? Why is there a linear unitary evolution? Where do Hilbert spaces come from? So that's going to be the thrust of the talk, providing answers, making assumptions, and on the basis of those assumptions, providing answers to some of these questions. Very good. The starting point is ontological clarity. From the beginning, we have a clear idea of what's going to be real in this model and what's going to be epistemic. We are going to take the microstates of the theory to be ontic, and for simplicity, because we can actually do it for in more general settings, we are going to assume that these ontic microstates are discrete. So we have n possible ontic microstates. This could describe something like a die, an n-sided quantum die. We may not know what is the phase of the die that came up. But there is at all times, there is a definite side phase that is up. So put in other words, we might not know which slit in a double slit experiment the particle goes through. We do not know, but the particle goes through one or the other, very much as in the, for example, the Bohmian approach, discrete ontic microstates. The probabilities, however, are completely epistemic. We're going to write the probability of the phase J as rho J, because we're going to want these guys eventually to be coordinates on a manifold. The probabilities are going to be completely Bayesian, but not personalistic. They're not. These probabilities do not reflect my own personal beliefs. They reflect the beliefs of some idealized rational agent. So this is much more in the direction of the objective probabilities, similar to those of Ed James. And definitely they're not quantum probabilities. I refrain from calling these probabilities classical probabilities, because in this kind of context, there is only one type. There are no quantum probabilities at all. So it's just a single and neither classical, it's just probability theory. Very good, our goal. Our goal in this talk is going to be to study curves on an n-1 dimensional simplex, on the space of probability distributions. So here is the simplex, the space of states with positive probabilities that add up to 1. And I should emphasize that I'm only going to be discussing kinematical aspects today. The reason is that while I want to study curves, but to do dynamics, it's not just a matter of studying curves on a space. You also have to study trajectories, which means that the parameter that labels points along these curves is supposed to be time, and the particular Hamiltonian that generates motion along these curves is supposed to be something that is connected with the actual clocks that you're using. So I'm going to just discuss a kinematical prelude to the true dynamics. However, we're going to see that a lot of the mathematical structure of quantum mechanics emerges at just this point. Very good. Some geometry. Here is the simplex, the space of probability distributions. A point in this space is a probability distributions. S is going to be the epistemic configuration space. The space of J's here, the microstates, that's the ontic configuration space. Here we draw a distinction between the two. That's a point. We're interested in curves. Curves have tangents to them. This is what eventually is going to describe velocities. The space of all possible vectors at that point is the tangent space at the point rho. And the space constructed with this base space S plus all the tangent spaces at all points is the tangent bundle. Very good. We can also invent another bundle, which comes from looking at the basic simplex, the base manifold, and discussing functions on it instead of curves. And we can discuss what happens with those gradients, or how do we describe the gradients of functions at that point. These are covectors. This is going to be the cotangent space at the point rho. And the question that here arises is, how are these covectors connected to vectors in this space, the tangent vectors, the velocities? In classical mechanics, we have a criterion for that. We associate the momenta, which are the objects that populate the cotangent spaces. We obtain those from Lagrangians. Here, we do not have a Lagrangian. That's the point of deriving these kinematical considerations and eventually even dynamics purely from probabilistic considerations. Here, we do not have a Lagrangian. So what we're going to do is we're going to decide right now that this problem has been solved, that there is such a thing as a covector here that is singled out. The precise argument of how you single out this covector is something that comes from studying the dynamics. Entropic dynamics is the framework that will allow you to do that. Here, we're just doing the kinematics that corresponds to an eventual entropic dynamics. Let us assume we know then what are the privileged covectors that are associated to the point rho. Very good. Just to tell you or give you an indication of where this is going, this space, the cotangent bundle, which consists of the base manifold plus all the cotangent spaces, is going to be the epistemic phase space. Phi is going to be the momentum that's canonically conjugate to rho. And again, to tell you more or less where this is going, eventually, this phi here will be the phase of the wave function. And this rho, of course, is going to give you the magnitude of the wave function. So this is how it is that these various quantities are being set up. But right now we have no dynamics. We do not know that we don't know anything really. It's just we have the geometry of this cotangent bundle. As a matter of notation, we're going to say that a point in this phase space is given by n coordinates for probabilities and another n coordinates for the phis. We're going to use a kind of composite index to denote whether you're talking about rhos or phis. Alpha tells you phi or rho, J tells you which phase of the die. We're going to have vectors in this space, and we're going to use Einstein's summation convention to describe them. The velocities are going to be given, vectors are going to be tangents to curves. Tau is the parameter along the curve. And I call it tau so that you see that eventually in some other talk, this tau would become time. We also had gradients. I used the tilde to denote the gradient on this cotangent bundle, which includes components along the rho direction and along the phi direction. And we can also express it in this way. Now, there is an important technicality here. It's going to turn out to be absolutely crucial in its consequences for quantum mechanics, namely that we're dealing with normalized probabilities. What that means is that if you look at, say, partial derivatives, such as these, this would assume that you're taking derivatives with respect to rho j, keeping all the other rho's constant. But if you have a constraint like normalization, you cannot do that. The rho's are not independent. So this technical problem is going to be solved in a rather general way by embedding the simplex of normalized probabilities into a larger space, which is like the positive cone of unnormalized probabilities. So I am really adding a degree of freedom when I do that. And of course, when I add a degree of freedom for rho, I'm also adding a degree of freedom for the corresponding phi. So our space here is going to have 2n dimensions, while we're really interested in a space of 2n minus 2 dimensions. So this extended simplex, the positive cone, is this space here. Very good. We're going to be discussing now more about the geometry of this cotangent bundle. We're going to first discuss the symplectic geometry and see some of its consequences. And then we're going to describe its metric geometry and see what its consequences are. But notice, I'm not doing physics here. This is just the geometry of these funny spaces of probabilities and their cotangent spaces. So we have a symplectic form, a privileged tensor. Given rho, given phi, we can always construct that. And if you apply this tensor to two vectors, we can write it in component form like this, Einstein summation. These guys have been summed over, where the symplectic form takes this standard familiar form. Very good. We are going to be interested in vector flows, vector fields. I use bars to denote a vector in the cotangent bundle. We're going to be interested in these vectors such that as you flow with them, the symplectic form remains fixed, is preserved by the flow. I'll mention in a little while, it will become clear why these are called Hamiltonian flows. The derivative that appears here is the Lie derivative. If you're familiar with it, great. If you're not so familiar with the Lie derivative, well, it's basically just a fancy version of taking directional derivatives in curved spaces and of general tensors. So this just says that the directional derivative of the symplectic form along the direction defined by this vector is equal to 0. So we're going to look at those vector fields that preserve the symplectic form, and these guys have an enormous significance for physics. Although now we're not doing physics, it's just geometry. This is going to be one of the central equations in the whole thing. By Poincaré's lemma, there is then a scalar function that I'm going to call h tilde. This is a scalar function on the cotangent, on the phase space, such that, and here we have a formula, the application of omega on that vector is the gradient of a scalar. In English, this would look like, or could be translated into, if the curl of the vector h is 0, then the vector h must be the gradient of a scalar function, h tilde. Very good. This is the more general way to say it. And if we translate this into components, what we get is something truly remarkable, because we have here that the rho dot is the derivative of the h with respect to phi, and phi dot is the derivative of h with respect to the coordinate with a minus sign. These are Hamilton's equations. This is why we call the vector H, we call that a Hamiltonian vector field, and H tilde is the corresponding Hamiltonian function. So if you just restrict yourself to flows, to Hamiltonian vector fields that preserve the symplectic form, the curves that will achieve that are such that there is a Hamiltonian and you obey Hamilton's equations. Furthermore, if you apply this symplectic form to two Hamiltonian vector fields, this is going to be equal to the Poisson bracket of the corresponding Hamilton functions. And furthermore, I'm going to use this equation in a second, the time derivative, the tau derivative of any function in the phase space is going to be given by the Poisson bracket with the Hamiltonian. So you can see how an incredible amount of the structure of physics, the structure of classical mechanics, is coming from purely geometrical considerations. This is central because while these are purely geometrical considerations, it stands to reason that it might not be just limited to doing classical mechanics. And that's exactly one of the points I want to stress in this talk. This kind of formalism, the classical Hamiltonian formalism, applies to quantum mechanics as well. Let's go back to the normalization constraint. I'm going to write the normalization. Here we're using the fact that we're moving in a space of probabilities, right? So probabilities are normalized. We embedded our probabilities in a larger space just because normalization is such a hassle, but we cannot ignore it. So here's the normalization of Rho. We're going to write the normalization in terms of a scalar function. So of course, the constraint of normalization is that this scalar function until it vanishes. This is a constraint. Very good. That's going to be central because it says that nx, the scalar function n, generates itself a Hamiltonian flow. So this is the Hamiltonian function for a Hamiltonian flow. And if we write out what that is, we find that as you move along the vector n, the probabilities, nu is the parameter along these curves, the probabilities do not change. But these momenta, these phases do change by the parameter nu, which is independent of j. So what we are seeing here is that if you change the phases by a constant, you generate an equivalent point in the space. In other words, we have, by introducing an additional probability degree of freedom and dealing with unnormalized probabilities, we have implicitly increased the number of degrees of freedom by 2, one probability and one momentum. We eliminate the additional probability degree of freedom by imposing the constraint on n. And we eliminate the additional degree of freedom on momentum by declaring that this phase here and that phase there are going to be completely equivalent. Let's do that more formally. We would like to have Hamiltonians that preserve normalization. But if NH is 0, then HN is 0. If N is conserved along H, then H is conserved along N, which we write like this, dH d nu is 0, which means that N generates a symmetry. In fact, it is like a gauge symmetry. And in quantum mechanics, this is manifested as saying that if you change the phase of your system by a constant, then you have an equivalent state, an equivalent epistemic state. And this is what is manifested in the language of quantum mechanics as saying the states of the system are represented by rays as opposed to by vectors in the Hilbert space. The other thing that appears here, of course, is the fact that H itself is gauge invariant, which is expressed in this equation here. This is going to be important towards the end of the talk. Very good. Having dealt with the symplectic geometry and the normalization constraint, now we deal with the information geometry of this phase space. Now, this is what is important here. Manifolds in general do not come equipped with a geometry, with a metric tensor. The glorious exception is the statistical manifold, spaces of probabilities. These come automatically endowed with a metric tensor. Being a statistical manifold, there is a natural metric tensor, and it's rather unique. This is important. Well, without one qualification. There is a metric tensor that comes from information geometry considerations, and the metric tensor is going to be given by an expression of this form, where A and B are almost arbitrary functions. So the metric tensor of the extended statistical manifold of unnormalized probabilities is rather general. It's a general spherically symmetric space. This has an interesting hidden symmetry here, not at all apparent from the way I've written it here. In these coordinates, it doesn't look that spherically symmetric. The space of normalized probabilities is actually a sphere. So when you put rho equals 1 here, the normalization of rho equals 1, the object that appears is a nice sphere. Very good. So we do have a metric structure for the statistical manifold. But the phase space is not itself a statistical manifold. There are all sorts of cotangent spaces floating around there too. So we would like to extend the metric structure of the underlying space of probabilities to the full phase space. And the way we do it is we're going to require that the metric tensor of the full phase space be determined uniquely by the metric tensor of the underlying statistical manifold. And here we go. For the 2n dimensional phase space, we are going to require that the metric tensor, when restricted to vectors in the direction of the base space of rows, be exactly the same that we have here. We are also going to require that when you restrict itself to the co-vectors, these guys are co-vectors on the statistical manifold, that the scalar product also be exactly the same that you would have if you just were dealing with the statistical manifold. There is an additional piece that you could add, which is determined by the constraint that you're just dealing with the same metric tensor, which includes mixed terms, and there could in principle be a constant there. Very good. So this is the most general metric that one could write for the phase space, implied by the condition that the metric of the phase space be determined purely from the fact that the underlying base space is a statistical manifold, a space of probabilities. Now I'm gonna make an assumption that comes from physics, okay? The motivation is going to be the following. We're trying to study curves on this statistical manifold. We would like to have the situation such that if you have a curve that flows in a particular direction, you could also have a curve that flows in the opposite direction. You can traverse the curve one way or the other, and which would be a kind of, with the same velocities, right? We would like to have a kind of flow reversal symmetry. Since under flow reversal, you have heard this under the name of time reversal symmetry, right? Under flow reversal, the changes in the coordinates and in the momenta go in opposite directions. There is a minus sign for the momenta. So if you impose flow reversal, then imposing flow reversal amounts to setting that coefficient equal to 0, in which case that disappears, and this is going to be the metric tensor for the phase space. Now, I should remark very quickly here that the fact that I am imposing flow reversal symmetry for the phase space does not mean that I am imposing time reversal symmetry for the whole theory. With these kinematics, one would like to describe systems that have different interactions. Some of those interactions may violate time reversal symmetry. Some other interactions might preserve time reversal symmetry. So what we would like to do at this stage of the game is we're going to want to have all those violations to be due to the particular choice of Hamiltonian. The Hamiltonian is going to have pieces that describe, say, electromagnetic interactions that preserve time reversal. And it's going to have other pieces that include, I don't know, a Kobayashi-Maskawa matrix or something like that, that includes time reversal violations. So what we are allowing when we say the phase space allows for flow reversal symmetry is we're preparing the ground for having complicated Hamiltonians. Some of which pieces will have pieces that preserve flow reversal and others will not. So that's the justification for the beta equal to 0. Very good. We're almost done here, but famous last words, right? There is still plenty to go. We're not interested so much in the geometry of the embedding space of non-normalized, unnormalized probabilities. We are really interested in the space of normalized probabilities. So we want to figure out what the metric is for the space of the subspace, the submanifold of normalized probabilities. So we're going to impose that we're now on the simplex of normalized probabilities, and we're going to consider the distance between 2 points in phase space. But we just saw that if you were to displace these phases by a constant, you would have an equivalent point. So what we're really trying to figure out is the distance between 2 rays. And the distance between 2 rays is going to be given by, well, the metric tensor, where here in the place where you have the momenta, you have the possibility of changing the point sliding along a given ray. And we're going to define the distance between 2 neighboring rays as the minimum of this distance here when you allow nu to change. So if you see my hand, you have 1 point there, and you have in 1 ray, and you have another point, and you allow that to slide over the ray, and we're going to try to find the minimum distance. And when you do that, you get an expression. There are two, it's a messy expression. Don't even try to read it too carefully, but there are two features of this expression here for the distance that is induced on the phase space of normalized probabilities. There are 2 features here that are really important. One of them is that this is an unusual way to write the Fubini study metric. It has nothing to do with quantum mechanics. Fubini and Study wrote down their metric in 1903, 1904, way before anything, right? What is new about all of this derivation is that the Fubini study metric here has been derived from considerations of information geometry. That's the new element in this derivation. The other amazing thing that's going on with this formula here for the Fubini study metric is that, remember there were 2 arbitrary functions here? A has disappeared and B only appears on the normalization constraint surface. In other words, the particular embedding into the phase space of non-normalized probabilities does not matter at all. are curves that we're really interested, moving in the spaces of normalized probabilities, do not depend on what the embedding, the larger spherically symmetric space. So we're going to make a very convenient choice. Just set A equal to 0 and B equals to 1. Completely arbitrary, really. I mean, in some publications, I have written B as normalized, the chosen, the function B as being H bar. So it's just a matter of the units you want to use for your distances. The amazing thing about this choice is that it makes the embedding space particularly simple. It's a choice, but if there is a simple choice, why not make it? After all, our quantum dynamics will never probe these regions outside of the normalized probability submanifold. The fact that this is flat is very significant because this is going to be the Hilbert space. But let's proceed. Here is our metric. Then for the embedding space, with this particular choice, this happens to be a flat space. And of course, we can also go write it in terms of the components of the metric tensor. We can write it in this form. And once we have the metric tensor, we can do something that's pretty amazing, which is we can use the metric tensor to lower indices and raise indices. So suppose we take the symplectic form and we raise, take the inverse of this guy, raise the index, and we obtain, there is a minus sign there that's convenient for conventional purposes. We raise the first index here, and we get a tensor that acts on vectors to produce other vectors. And here's that tensor. And this tensor has a remarkable property. Namely, if you apply it twice, you get minus the identity. So what this is saying is that once you have a symplectic structure and you have a metric structure, you also have a complex structure. So by imposing a symplectic structure on our phase space, and then imposing a geometrical structure coming from information geometry, we have automatically introduced a complex structure into the picture. This is the reason why we use complex numbers in quantum mechanics and not say quaternions or octonions or whatever other field. These spaces are called Kähler manifolds. What we are doing here is dealing with a particularly simple type of Kähler manifold where the metric structure is coming from information geometry. And we're dealing, of course, with statistical manifolds. Now that we have studied the symplectic structure and the geometric structure, the metric structure of this space, I'm going to do something that is necessary for quantum mechanics. So this is the second installment of this set of assumptions that invokes a little bit of physics. You see what happens with the theories of inference is that the same theory of inference ought to apply to the stock market or to ecosystems or to medical trials and also to quantum mechanics. So at some point in the derivation of these theories, I have to tell my inference machinery that, hey, we're not dealing with the stock market here. We are dealing with quantum mechanics. So this is one place where we have to make an interesting redefinition of the choice of cotangent space. Here we have our base manifold, the standard simplex of unnormalized probabilities. That's a point. The tangent space, the cotangent space there is this flat space. And so that's the cotangent at the point rho. And we now learned that there is a complex structure here. So to see how we redefine our cotangent spaces, I'm going to introduce complex coordinates. And here you have the complex coordinates. This is the new coordinate, the wave function. And this is its canonically conjugate momentum. The transformation from rho phi to psi and this momentum is actually canonical. So that's what determines the form of the conjugate momentum. This is a canonical transformation. A point in the phase space now is going to be given by its coordinate components and its momentum components. And the complex structure is now given by this tensor that takes a very unique form, which amounts to saying when you apply this guy to something like this, you multiply the wave functions by I, as you might expect, and you are multiplying the complex conjugates by binoside, as you might really expect. So complex coordinates appear to be very natural in this setting, but of course, the way the complex coordinates work is that if I take a phase here and I add 2 pi, I end up describing exactly the same point on the phase space. In other words, phi and phi plus 2 pi are equivalent to each other. Phi is an angle. So what we are doing here is we are saying the cotangent space is flat, but opposite faces that differ by 2 pi, opposite faces of this square, are identified. We have to do this in both directions. In fact, the cotangent spaces are hypercubes of coordinate length, edge 2 pi, with the opposite faces identified. This redefinition of the cotangent space is crucial for quantum mechanics. It's going to be saying something like, if you have canonical momenta, here the phi's canonically conjugate to rho, the phases can be multi-valued. You can increase always by 2 pi, 4 pi, and so on. But the wave functions are going to be single valued. That's what's being introduced in this by this assumption, by this redefinition of the cotangent spaces. Very good. We're almost there now. We want flows described by either the vector H or its associated Hamiltonian that preserve not only the symplectic form, but also the metric form. These flows are such then that they're going to be Hamilton flows, and they're also going to be killing flows. These Hamilton killing flows, when you impose both of those conditions together, are such that second derivatives of H with respect to the psi's are 0. And second derivatives of H with respect to psi star are 0 too. So this is what this means, is that the Hamiltonian functions we seek are going to be bilinear in the H's, in the psi's. There could be linear terms also, but those are discarded by gauge invariance. So the gauge invariance we talked about earlier is crucial to get to this form. And this leads me to my final slide. The flow, the Hamilton killing flows are given by Hamilton's equations. We can write the Hamilton equation in the standard form, just differentiate with respect to the momentum, you get the psi dot. Or you can write it in the Poisson bracket form. Either way, when the Hamiltonian is bilinear, the result is the, just differentiate with respect to the psi, and you get the rest, right? The result is the Schrödinger equation. And it's linear. It's the linear Schrödinger equation. So this derivation explains the linearity of the Schrödinger equation. I should also say that because this is a linear Schrödinger equation, if you were to transform back into the rho psi coordinates, you would see the emergence of a quantum potential, which is what's responsible for all the non-localities and everything that there is in quantum mechanics. Very good. To summarize and conclude, the first and most crucial step is ontological clarity. the microstates, we decide on a set of ontic microstates, and then we try to fool around with the dynamics of probabilities. We never talk about the dynamics of the microstates. We're just talking about the dynamics of probabilities. The phase space is a cotangent bundle. The cotangent bundle takes the form of a simplex plus all the cotangent hypercubes. And this is what leads us to a definite symplectic structure. Information geometry leads us to a definite metric structure. The two together lead to a complex structure. Imposing Hamilton killing flows that preserve these things leads to the linear Schrödinger equation, so that quantum states, the epistemic quantum states, the wave functions really, that represent the state of the system, are raised in a Hilbert space that's essentially optional. It had to do with that embedding space that was introduced purely for calculational purposes. And they obey the Born rule in the sense that, yes, of course, if the magnitude of the wave function is the probability, then the Born rule is automatic. Thank you very much. I have not mentioned references. Okay, I would like to start by thanking all the people that have over the years been involved in the development of this program. I have not stated many references, but this particular presentation appears in this paper, and there you can find in the archive, you can find all my papers, and here in this paper here you can find all sorts of reference to the work of other people. Thank you very much.
Many thanks, Ariel, for this great presentation.
Did I go too much over time?
No, it's fine. I think it's fine.
I always have this problem because you see, I have to state like 6 or 7 assumptions, and once I have the assumptions under control, then I can give the whole talk in 2 minutes. But
yeah.
Anyway,
the geometrical background is
absolutely
is demanding. So, okay, if there are any questions in the public, please let me know by chat. In the meantime, I will ask you some questions because perhaps I have too many questions about this. So one of them is, I'm puzzled about the geometry of the state space that you create, because you talk about a simplex at a point, but then you say that when you particularize to quantum mechanics, then you obtain a complex structure. So my question is, what is the shape of the object that you create? Because in quantum mechanics, we know the shape, which is, it is the projective geometry associated to a complex Hilbert space, which is a sort of Kähler manifold. So what you obtain is something which is isomorphic to a Kähler manifold.
Well, actually, the embedding, when you choose this embedding space, the phase space of unnormalized probabilities, that's Hilbert space.
Ah, okay. It is exactly Hilbert space.
It's exactly the same thing.
Well, it's the projective geometry, or yeah.
Once you have the Hilbert space, it's a linear flat space. Yes, all of that. But then when we do physics, we do not use the whole Hilbert space. We just talk about the rays on the Hilbert space.
No,
right?
I agree. Yes.
And that's what's emerging here.
Okay, so yeah, so you embed it in the projective geometry of a Hilbert space.
That's right. Yes.
Yeah,
but I would like to emphasize that the Hilbert space itself is just a convenient construction. It's extremely convenient because once you have a linear Schrödinger equation, if you could take advantage of that linearity, that would be great for calculational purposes. I mean, the whole of physics is based on calculational methods that take advantage of the linearity of the Schrödinger equation. But if you take the Schrödinger equation and you impose that the states be normalized at the level of the Schrödinger equation, then all the advantages of linearity go down the drain, because you take 2 states and you can superpose them, but the superposed state is not going to be normalized. So you have to play all sorts of additional games there to renormalize and do all sorts of weird things. So the normalization constraint really spoils a lot of the beautiful simplification that comes from dealing with unnormalized probabilities.
So, and regarding that, you mentioned at some point that you allow for the freedom of having a non-time reversal symmetric evolution, right? So my question is, okay, what's the meaning of that? Does it mean that somehow you will be, if you allow for a I mean, let us call it motion reversal, right? If you have, because you have it predefined. What's the meaning? Once you define the phase space, you know how to reverse motion there. It is previous to specifying the dynamics, right? So, but if you allow for a non-time reversal dynamics, will you get something like the measurement process, something like something that can decohere to something or something like that? What's the meaning of that?
Well, for example, okay, actually, one of the weird things about this kind of approach is that you get quantum mechanics, period. So for example, if I do the same approach and I do the dynamics, everything, for a particle with spin, what do I get? I get the Pauli equation. It's very nice, very nice. And of course, just the inference process does not completely determine what the Hamiltonian is going to be. So the Hamiltonian could include electromagnetic interactions, and it's actually very easy to see how it is you can introduce electromagnetic interactions. And it could be very well be that your particle has a magnetic dipole moment. Perfect. That's what you want if you would like to describe the electron or you would like to describe the proton. Great. Or even the neutron. You can do all of those. But it also offers the possibility of giving the particle an electric dipole moment, which violates time reversal invariance. So it opens up the possibilities for any kind of interactions you might include there, including ones that violate time reversal. The phase space is symmetric, but the actual Hamiltonian flows can be chosen to not to be. I should say that one of the things that sometimes people feel a little bit disappointed in is the fact that when I do a theory of this type, I get exactly quantum mechanics, right? And say, okay, oh, there is nothing new. Well, I would claim that there better be nothing new. When I do this theory at the non-relativistic level, if you discover any deviations from quantum mechanics, you're in deep trouble because quantum mechanics has been tested so well. You should only expect deviations from quantum mechanics if you were to do something where our conceptual understanding of the physics is a little bit shakier. So if you try to do quantum fields in curved space-time, then you could find differences. And indeed, if we do the scalar fields propagating in a background space-time, we get quantum field theory, period. That's it. We don't get any, it's just quantum field theory on a curved space-time. Fully relativistic and all, no big deal. But if you make the space-time dynamical, in other words, if you have this quantum field theory interacting with gravity, fully with a dynamical gravity, then you get differences. You get violations of quantum mechanics. You still have Hamilton killing flows. You still have all of that, yes. But the Schrödinger equation, the Schrödinger functional equation is no longer linear. And so I would say that we have here a prediction of this type of theory. Quantum mechanics and its attending Hilbert spaces will no longer propagate in unitary, according to a unitary evolution, once you start including gravity into the picture.
Okay, yes, thanks. I see that with this framework, you have a lot of more freedom to deform the thing when you jump outside. I mean, the non-relativistic setting.
Oh, yes.
I mean, yeah, okay, plane. But my previous question about non-reversibility has to do with this. At the beginning of the talk, you mentioned that the trajectories or the positions are real or determined, or like
yes,
like the moment, but the rest of the observables are not. So what do you mean by that? My question is, isn't it possible to use these non-reversible, time reversal symmetric evolutions to model what happens in standard quantum mechanics during the measurement process? How do you cope with the measurement process?
Okay, the answer is absolutely yes. But the time irreversibility that matters in this context is not the time irreversibility that comes from the beta parameter, setting beta equal to 0. Not that. Not that. It comes from deciding. I would like to say two things here. First, how do you do a measurement of, say, momentum in this theory? All that's real is position. How do you measure momentum? Well, you measure momentum by measuring position. Very much in the spirit of how do you measure spin? You measure spin in a Stern-Gerlach device by measuring position. So in the end, all measurements are positions. That's the only thing that's ontic. And this is what solves the measurement problem. You only have positions. Positions are definite at all times, unknown, but definite. So you just measure them like Stern-Gerlach. Momentum, well, you have a wave function coming at you. You put a magnetic field. Different plane wave components are going to be scattered in different directions. Then you measure the position of the particle, and from there you infer what the momentum could have been earlier, right? It's all a matter of inference. Rather than observables, one could call them inferables.
I see. So it is a sort of point in common with modal interpretations that have somehow a preferred algebra that is actual and the rest is only potential, like in Olympia's interpretation or tennis works. And
absolutely. Okay. Yeah, and when by model you say model with the whole quantitative set of instruments that come from information theory, probabilistic theory, when you really put your probabilities to work, and you have statistical manifolds with information geometry, and the updating is going to be induced by using entropies, and you really use all that machinery of probability theory, then yes, you do get models that solve the measurement problem, no problem.
I see. I see. Now I understand better your move. Yeah, I see.
And then there is, you see, this is the first half of a talk. The first half is purely kinematics. The second half is about what do you mean by time in such a picture? You see, probability theory tells you nothing about time. The same probability theory can be used for the stock market or ecosystems or quantum mechanics. But it can also be used for things that are completely static. You can predict the future, you can predict the past, or infer the future, infer the past, right? It's completely atemporal. A fully dynamical description requires that we care about time. So caring about the nature of time is not something that should concern us only when we're dealing with special relativity or general relativity. Actually, it should concern us in quantum mechanics as well, right? And the entropic dynamics part of this program is the one in which we care about what do you mean by time? How do you define time? What do you mean by an instant? Are these instants ordered? What is the separation between successive instants? How do you define duration? That part of the program is really what makes the theory dynamical as opposed to just the kinematics. This is the kinematics skeleton of the theory. By the way, in that approach, time ends up being, there is an arrow of time because successive instants are induced by maximizing an entropy. So there is a notion of an entropic time for it, but that's another topic, right?
That's another in for the next conference. And I
the
hope
next
that
one, yes.
in the next one,
yes.
you can come back to Argentina. Okay, Ariel, thanks.
Oh, I will, definitely.
So
yes, count me in.
Thanks for being here. And so we close this morning section now, but don't forget that later in the afternoon at 2 o'clock Argentina time, we have the poster session. So you are all invited to come. There will be separate rooms where each participant will be presenting their posters, and you can ask them and have some chat and ask for details of their presentation.